All right, we're on 10.3, which is exponential modeling day 1. Today, actually, our objective is that you will be able to write an exponential function when there's an increase over time. This is what we mentioned in 10.1 known as the exponential growth. So exponential functions are important, primarily because of the usefulness in modeling a variety of real-world phenomena. Now, in this lesson, we're going to explore the increase of functions, things that are increasing over time. So in our first example, let's just take a simple basic look at this. It says, suppose you deposit money into a saving account that receives 5% interest per year on the amount of money that is in the account for a year. Assume that you deposit $400 into the account initially. So you went to the bank and you put $400 into the account. How much of the savings will you increase? How much will the saving account increase by over a course of a year? So remember, in this year you have $400 and then you know that it's going to be increased at 5%. 5%, remember, we need this as a decimal, which is actually 0.05, which is 5% is 5 out of 100. I need it as a decimal. So it's the 400 that was in my account times this is the interest that I'm getting. This is the 0.05%. This is actually $20 you're getting in a year. So if you put $400 in your account over 1 year, you will get $20. Then it say how much money will you have at the end of the account. So you will have that 400 that you started plus that $20 interest. So your grand total at year 1 is going to be $420. Now this is where we're going to start to make inferences. By what single number could you have multiplied 400 in order to calculate the answer in part B? So this is where you think. You say, what do I want to do? What did I basically do? I took the $400 plus I did the interest, which was the 400 times the 0.5. And this is actually what gave me that 420, right? So I want to think. This 400 is actually a whole, right? This 400 is a whole. Now what I can do with these two, I can take the 400 out. What's left over? What is left over from this? 400, this is a whole plus the 0.05. And then this will actually give me 400, 1.05. So all I can do to get to this 420 is to multiply this number, the entire number, the 400, by 1.05. And again, how did I get this? I started with the 400 and then I added the interest. If you look at this, they both have a 400 in common, so I factored it out. When I take 400 out of 400, you would have, 1 is left, and then I take 400 out here, 0.05 is left, and then I would add them. Why addition? Because that's what I did. If I'm earning interest, that's what that's what I'm gonna get. Now it says use your answer from C, determine the amount of money 2 years and 10 years. So think of it now. How can I do this? So 400, and I want to multiply this by 0.05. So how many years? 2 years. You put this entire thing in the calculator, you will actually get 441. Now what if it was 10 years? 400, same thing, 1.05, but now I'm going to the 10. And this will give you, and it's rounded to the nearest cent. So this will give me 651.56. So notice that these two here are known as the number of years. That's why this is like saying it's to the x power. That's why it's an exponential function. F. How can I write an equation S of t so that I have a function? So S of t is equal to 400 times the 1.05 to the t power, where t is the number of years. So however many number of years the question is asking me for, I can go ahead and just plug it in. Like here I plugged in 2 and then I plugged in 10. F, the last one says, using a table on your calculator to the nearest year, how long will it take for the initial 400 to be double? Provide evidence. So if 400 is being doubled, I know it's going to be somewhere about around 800. So what am I going to do? Let's get our calculator and enter that function. All right, so I am graph. I want to enter my function. It was 400 and then it was 1.05. But remember, the calculator can't read t, so we're going to use x. Enter. So don't worry about, you're not going to see the graph. What we want to do is go to table. And I want to know, when is this going to be? Somewhere around 800. So keep going up. So you know it's going to be somewhere between 14 and 15 years. It's going to, at the starting of 14 year, it's going to be 791. And then in the 15th year, it's going to be $831.57. So where is this going to be? When is this going to be double? That's what the question is asking me for. When is this going to be double? So it's going to be double sometime in the 14th year. So it'll take 14 years for this $400 to become 800. And all I did was enter the function, go to my table at 400. This is what my starting amount is. Go down to where I see somewhere between close to 800, and it's going to be between here. So you know, at the beginning of the 14th year, it will be 791. Let's say about, you know, at the end of the 14th year, 15th year, you're starting with 831. So you know it has to be by the end of the 14th year. That's when I'm going to get that money doubled. All right? So now, during that process, you have to think about an exponential increasing function. This is something, again, and you're going to see it, sometimes you might see it as exponential growth, because the amount is growing, it's increasing. It's at a fixed amount, so it's whatever your starting is, which is q of 0. That's your starting amount, your present amount. In this case, it was $400, so this is my q of 0. It's always going to be 1 plus p. P represents the percent that it's going to be increasing per year. So in this case, my P was 5%, and it's always going to be T. So this is like a formula you need to know. Exponential. Your starting amount, and then 1 plus whatever percent. And this P is always in decimal form. Super important. So here it says, which of the following savings has an account of $250 invested on interest rate at 3? So my starting is $250. I know it's going to be 1 plus 3%. How do we write 3% as a decimal? 3 over 100. Control Enter, 0.03. So I am going to go ahead and add that. It's always going to be to the sum t time, and this again is s. And let's get this. 250 is equal to 1.03 to the t power, which is choice 2. Okay, so remember this formula. Let's look at another example. So there are many other real-world phenomena. They use this for exponential increasing patterns. So a good example is about population growth, which is studied over a long period of time. It's typically at a fixed rate. So this is how you can apply this to actual real life, and this is what people do. Exercise 3 says the population of fruit bud NY is increased at a steady rate of 2.5% per year. In order to plan for school growth, the town would be able to mathematically model the future population of the town. At the end of 2005, fruit bud have a population of 65,000 residents. Now, first question say write a formula P so we can model this. So the first thing, and even before thinking about formula, what is 2.5? 2.5% is 2.5 out of 100, which is actually 0.025. That's my first step. What's my starting population? It's going to be 6,500. 1 plus 2.025 to the t power. And I want to just simplify this. So P is equal to 6,500, 1.025 to the t power. So this here is my exponential function. B said to sketch a graph that looks like this. Sketch a graph on the axis below. So what you want to do, and this is where you're going to go ahead and do this on your own, change the window side. This should be 2,400. I'm sorry, 24,000. This will be 50. And I want you this, we know that this graph is starting at 6,500. That's my initial start. And then you will see a graph that looks something like this. Yours will look way better than mine. And here we don't need an arrow because we're going to stop at 50. It asks for 50. So at this point we're going to stop, and you should check what is this value. This value is actually 50,22341. Why does that look a little off? Let's double check that number really quick. Do me a favor, double check this number for me and make sure I am correct. Actually, I am 52,22341. This is the point. When it's 50, that's where I'm stopping. It's that point. Now, C says use the model from your A, which is here, to predict at the end of 2010. So I am, and I'm going to just write here, I started at 2005 and I want to go to 2010. How many years is this? This is actually 5 years. So what I'm going to do, P is actually going to be 6,500, 1.025, and this is where it comes in 5. Put that in the calculator. It's approximately 7,354 people. That's the population. D says determine the year that the population reaches a 10,000 mark. At a 10,000 mark, show this on your diagram. So you want to know, if I have this right here, this is my 10,000. What is this point right here? This is what I want to ask. So let's get our graph in calculator. So delete everything here, and I want to go back to my graph and enter the function. The function is 6,500 times 1.025 raised to the x, and then we need to change the window settings. We said, right, we wanted the x minimum to be 0, 24,000. Oopsie. The y, no, this, sorry, the y max is 50. This is actually everything out. The y minimum is 0, and here it is 24,000. Enter. So you have this graph. Now, menu, I want to go to my table, and I want to know somewhere, when is this y is going to be 10,000? So I keep using my graph, keep going. If you notice, it's somewhere between, somewhere between 17 and 18. But how do I know exactly where it is? 17 and 18. How do I know exactly where it is? Well, it's between 17 and 18, so it's fine. What we can do now is go ahead. I know I'm going to use I can't use 17 because then that has less than what what I'm being asked for. I have to use 18 because that's more. So in terms of population, if I ask you specifically for 10,000, then I need 10,000. I don't need 9,800. So this question is now going to say I started at 2005 and I'm adding 18 more years to this. When I add these two together, 8 and 2, 10 and 3, so this becomes in 2023, that's when I'm going to go ahead and get about 10,000. Oh, not dollars, 10,000 people. That's when the population is going to have 10,000 people. Okay? So again, I just showed you here at 50 the population is 22,342. So on the diagram, I actually forgot to put my comma in the middle. So it's saying at 50 it is 22,341. So just to clarify that when you put that on your graph. Now what I have like to do is our last two example, 4 and 5, before you go ahead and do your stuff. The number of students at a particular school who has the flu is increasing at 12% per year. Oops. At the beginning of Monday, there were 56 students with flu. Which of the following is closest to the number of students on Friday? So it's starting 56, and then what am I doing? It's going to be 1 plus 0.12 to the, I don't know, you can call it t, it doesn't matter, whatever you call it. Remember, 12% is 0.12, so this becomes 56, 1.12. So Monday, this is my starting, and I want to know when Friday, that's going to be my ending. So how many days? So I have Tuesday, I have Wednesday, and I have Thursday. So this will be 1, 2, 3, 4. So that's 4. Put this in your calculator. You will get 88.117, which is approximately 88. And that's how you see these questions on the regions. Very simple, straightforward. Know your formula. If the population of rabbits is 45 and it increased at 8% per year, 0.08, you know it's going to be 1 plus 0.08. Which of the following is the closest time to take the population to double? Good. Now this is one of those questions where we want it to be equal to what's double 45. This is 90. So now what you can do, plug in your answer. It's a multiple choice. So the first one I would do is 45, 1.08 to the 14th. What do you get? Does that give you something like 90? This is the question mark. 45, 1.08 to 22. Is that equal to 90? 45, 1.08 to the 6th power. Is that 90? And then 45, 1.08 to the 9th power. Is that 90? This is what you're going to check. You're going to do this and you're going to see the last one is approximately 90. It's just plugging in your answer choice. Your other way is to plug this in the graphing calculator and look at with these years where it's really close. I actually like that method, so let's take a look at that really quick before I let you go. So you go back to document, you go to graph, enter the formula that we just found, 45, 1.08 to the x, enter. I don't care if it doesn't show up, I want to go to my table. So the first one says that I'm looking for 90. So I'll keep going down. Where do I see something that's close to 90? If you look at it, 8.98 is the closest. And that's why when x is 9, that's how I got my answer as 9. Alrighty, I know it's been a long video, but I wanted to show you some stuff on the calculator on how to get this done. Go ahead, practice those problems, and good luck.